is we're doing this remote learning thing. So half of the beginning of these slides don't really mean anything now because we're not actually in class. Uh, Let me share my screen really quickly. I'm not sharing a window. So everybody should be able to see my screen. Everybody can see it? You just thumbs up. Okay, good. So this is the intro. And basically, again, it's just going to be intro and then the three things that I think are like really super critical that you all know, or just get a kind of little refresher that will help you immensely in this class. And those three things are fractions, exponents, and order of operations. And I'm sure if you've been in any other math class, these three things are probably on your list of like, man, I hate when we do fractions, or I hate when some exponents come up, or how do I put an exponent in a calculator, or which operation do I do first? So those are three things we're going to briefly touch on today. And again, this entire lecture will be uploaded on YouTube so that you can see it there too. But feel free to ask questions. That'll help future students when I send them this lecture. You all will be the ones asking questions on the lecture. So getting started, and this is what I was saying, that some of these things kind of don't really matter because we're doing this remote learning. So phone use should be kept to a minimum. I don't know, that's an odd one. Why was Thurgood Marshall in the meeting? Did you just see it? Was that like a hacker or something? Did you all see that? Am I tripping? You all saw that, right? That's odd. Okay, I wonder who Thurgood Marshall was. Wow. All right. Be sure to speak to the professor if any unexpected situations or obstacles arise. It's very important. Again, if we were in class physically, this would be what we would have done first week. I just didn't do it last week because I was having some problems, but this is what we would have done the first week. Another thing, do practice problems. Don't ghost mid-semester means even if you think you aren't doing so well, don't just disappear. So a lot of times what students like to do is they like to say, oh, there's no way, week 2, there's no way I can do anything in this math class, and they just disappear. They don't drop the class, they don't email me, they just stop showing up to class. Don't do that. So I'm a very, I don't want to say necessarily lenient, but I'm a very understanding professor, or at least I try to be. So if there's something that comes up, make sure you speak to me about it, and then we can figure something out to help you out. Then we got do practice problems, a lot of practice problems. That does apply to now. It applies just because even more so, I think, because if you're at home, it's going to be so important that you all do practice problems. It's going to be so important. That's really going to be what kind of helps you a lot. Doing practice problems, and then when you don't understand something, you can send me your practice problem, and you can send me a picture, an email, or whatever. Show me what it is, and I can help you along with that. Go to office hours, even though we aren't physically in the same space. Going to office hours still stands, just because you can email me, you can ask me questions, you can reach out, and that will also help you significantly in succeeding in this class. Respect the classroom and your classmates. I would say the only thing with the remote learning piece is just keep everything on mute as much as possible. Some people don't have a noisy background, but just in terms of like the echo and stuff, just try to keep your thing on mute as much as possible. And then lastly, ask questions. Don't be afraid to ask questions. I will not bite. I'm a pretty chill person, pretty chill professor. All right, so moving on, extra credit. We kind of spoke about some of this stuff last class. I told you all you need a scientific calculator. I think I showed you all one on Amazon, right? A little cheap one. Yeah, don't spend more than $20. In the open source textbook, I think I showed you the link to that. That link is in the syllabus. And then I'm not going to make it mandatory, but it'd be nice if you all could get a composition notebook, and that is where you do your practice problems in. But it's not going to be mandatory just because I don't have actually a way to see your composition notebook. Moving on, a little more about the textbook. So we're going to jump right into it. First thing we're going to talk about is fractions. And with the fractions piece, again, fractions is like the thing that holds up everybody. And we do need to have a pretty decent understanding of fractions to be able to succeed in this course. So here's just a little, I'm going to call it a 5-minute refresher on fractions. To start off, fractions generally represent parts of a whole or parts of a set. So right now, for example, a part of a set, I see that only 2 of you have your videos on out of 4 of you that are on the call, right? So that would be 2 out of 4, right? Another example would be if we had a pizza and, I'll draw a little pizza. We cut that pizza into 8 slices. We could take some of these slices and that would, represent a part of a whole. So we could take this slice, this slice, this slice, and this slice, and then each of us gets a slice. Well, no, actually we would need to take this one too. Then each of us would get a slice of pizza. And what fraction would this be? This would be 5 out of 8, right? So we took 5 out of 8 of the slices, so the fraction is 5 over 8. So another thing fractions can demonstrate is ratios or rates of change, right? Or basically, when we say ratios, what we mean is like a relationship between different things, right? A relationship between things. So for example, a relationship would be every 5 students will need 3 hours of tutoring, right? So we're saying it's 5 to 3. And we could write that like 5 students require 3 hours of tutoring, right? Or we traveled at a speed of 20 miles per hour. With speed, you're relating, it's the relationship between distance and time. It's how much distance you travel in a certain amount of time. So 20 miles per hour is saying that you travel 20 miles in how much time? In 1 hour, right? Or it will take 15 minutes to complete 10 problems. Which is basically saying 15 minutes goes with 10 problems. Same kind of idea. And then with rates of change, similar kind of thing as a ratio, but a rate of change is specific in that it's something that changes with time. So it's a relationship between how something changes and how much time passes for that thing to change. So that's what we mean when we say fractions as a rate of change. All right, so moving on. The general way we write fractions, we write it as one number, a little line, a number in the bottom. That should look familiar to everybody. The top number is called the numerator, and the bottom number is called the denominator. The numerator tells us how many parts you actually have. So for this fraction, 1 over 8, it's saying we have 1 part, right? And then you need to know, well, 1 part of what? Is it 1 part of a million, 1 part of 10, 1 part of 5, 1 part of what? And the denominator tells you the of what. So it's saying this fraction says we have 1 part out of 8 parts total. All right, that's what it's saying. And that's like the general thing that we're looking at. Fractions are the exact same thing as decimals. Decimals sometimes, no, I won't say that. Fractions are the same thing as decimals, and to convert from a fraction to a decimal, all we need to do is to divide, right? So if we have 5 over 7, if we wanted to convert 5/7, right, to a decimal, we just divide. What do we divide? We divide the top number by the bottom number. So we do 7 into 5, right? I'm sorry. Why won't it let me erase? It won't let me. Okay. Yeah. So we just divide. I don't like writing division like this. I almost never write division like this. The way I like to write division is, and this is going to kind of be like going in a circle. The way I like to write division is like this, right? I like to use the fraction bar to represent division. This is 5 divided by 7, right? Hold on 1 second, because I think I need to do this because it wasn't saving. Here we go. So yeah, I need to rewrite that. So again, to convert it, we divide. So we were doing 5 over 7. And then we divide the top number divided by the bottom number. Right? But like I said, I don't like writing it like this. I like to write it like this. This is 5 divided by 7. And I want you to get in the habit of writing division with a fraction bar. So almost every time we write division, we should use a fraction bar. We should not be using this symbol anymore, right? And we should definitely not be doing this anymore. Right? I mean, you could do this if you need to like work it out, but in general, we want to write division as a fraction bar and get comfortable seeing division written as a fraction bar, right? So when we divide this, and if you have your calculator already, you could pull it out and do the division. 5 divided by 7, what do you get? We get 0.714. We'll just leave it there, 0.714, right? And that's what this fraction is as a decimal. So all we need to do is divide to turn from a fraction into a decimal. So moving on, we need to talk about adding and subtracting fractions, multiplying fractions, and then we need to talk about dividing fractions. So let's start off with adding and subtracting fractions. So 2 key things, right? First thing is both of the fractions have to have the same denominator for us to add them together. Second thing is all we need to do is add or subtract the numerators, right? We don't actually do the same thing on the numerator and denominator. Once the denominators are the same, all we need to do is add or subtract the numerators. So let's do a little example. So there's an example in there, 2 over 5 plus 3 over 5, that equals 5 over 5. The denominators are the same, they're both 5, and our numerators, we just add them. 2 plus 3 equals 5, so we get 5 over 5. Let's do another example. What if the denominators are different? And again, we're not going to dig super deep into this because this is just like a refresher. But I will send you all some videos that kind of dig a little more into like finding common denominators and stuff like that if you need a little bit more of a refresher, right? So let's say we had 2 over 3 plus, 5 over 7. So what we need to find is we need to find a common denominator. The common denominator is a number that both denominators go into. So we need one number that both 3 and 7 go into. The easiest way to find one number that 3 and 7 go into is to just multiply 3 times 7. What is 3 times 7? 21, right? So now we rewrite both fractions with 21 as the denominator because, again, both 3 and 7 go into 21, right? And the next question we need to ask ourselves is how did we get 21 on this one? So how did we go from this 3 to this 21? What do we multiply by to get to 21? We multiply by 7. So we need to multiply the top number by the same thing. So we multiply the 3 by 7 to get 21. So we need to multiply the 2 by 7. And what is 2 times 7? 14. Same thing over here. What did we multiply the 7 by? What did we multiply that 7 right there by to get 21? We multiplied it by 3. Well, since we multiplied the bottom by 3, we need to multiply the top by 3. 5 times 3 is what? 15. Right? Now, all we need to do is add. So we do, what do we add? We add only the numerators. So we do 14 plus 15. What's 14 plus 15? That would be 29. And we get 29 over 21. So it's very straightforward. Again, you're just multiplying the two. That's the easiest way to do it. Multiply the two denominators by each other. And when we multiply those two denominators by each other, that will let us get what we call the common denominator. Right? So let's go to multiplying fractions. So to multiply fractions, all you need to do is even simpler than adding or subtracting fractions. To multiply fractions, all you need to do is multiply the numerators. You get an answer, that becomes your new answers numerator. And then multiply the denominators, get an answer, that becomes the answers denominator. So we have an example here. All you do is multiply the top, multiply the bottom. 2 times 6 is what? 12. That's how we got that 12. 3 times 8 is what? 24. That's how we got that 24. So we can do another example. So for multiplying fractions, we can do, let's do 5 over 8 times 3 over 9. 5 times 3 is what? So this is going to equal 5 times 3 over 8 times 9. So 5 times 3 is 15. 8 times 9 is what? 8 times 9 is 72. 72. Alright, so that's how we get the answer. Multiply across the top, multiply across the bottom, and we get our answer. So the last one, the last operation we need to do with fractions is dividing fractions. And to divide fractions, you flip the second fraction and then you multiply it, right? So we'll do this example here on the other thing. Well, let's just do it right here. So here we have 4 over 6 divided by 1 over 3. Now what we need to do is we need to flip the second one. Which one is the second one? The 1 over 3 is the second one. So we need to flip the 1 over 3, right? And we get 4 over 6, right? Flip the second one and multiply. So times 3 over 1, right? And then we multiply like regular. So 4 times 3 is 12. And 1 times 6 is 6. Right? So flip the second one and multiply. Right? So that's multiplying fractions, dividing fractions, adding and subtracting fractions. Right? All three of those operations are fairly straightforward. The only one that might give you some trouble sometimes is the adding and subtracting fractions. But just remember that they have to have the same denominator when you add and subtract fractions. All right, so jumping to the next thing. The next thing is exponents, right? What is going on here? Hold on 1 second. My slide looks a little messed up here. That's fine. I'll just move everything down really quickly. Sometimes when you upload the slides and download them, they might get a little corrupted. So it looks like that's what happened here. So with exponents, right? Exponents basically represent repeated multiplication. And we have two important parts. We have the base of the exponent and we have the exponent, right? So the base is the bottom number and the exponent is the top number, right? The exponent is the thing that tells us how many times to multiply, right? And the base tells us what to multiply by itself. So 2 to the third power is 2 times 2 times 2. Since it's to the third power, we're multiplying 2 by itself 3 times. So 2 times 2 times 2. It's repeated multiplication. So let's look at an example. Let's say we had 3 to the 5th. What would this be? Well, this would be 3 times 3 times 3 times 3 times 3. 5 of them, right? So that's 3 to the 5th. And I'm not going to multiply that out, but I could try. So 3 times 3 is 9, times another 3 is, what? Is 9 times 3? 27. Times another 3 is, what? What's 27 times 3? 81? Yeah, I think it's 81. 81, and then what's 81 times 3? What would that be? 160, 240, 243? Yeah. So that would be 243, right? But that's as simple as it is. It's just repeated multiplication. We're multiplying by the same thing multiple times. Now, when we do exponents, some interesting rules arise. So the first rule that we'll look at are the rules of 1. And these are called the rules of exponents. And the rules of 1, right? The first of the rules of 1 is that any number raised to the power of 1 equals itself, right? That's the first rule of 1. So an example of that, if we do 5 to the first power, what does this equal? That just equals itself, 5. If we do 10 to the first power, what does this equal? 10, right? If we do 2037 to the first power, what does it equal? 2037. So any number you raise to the first power equals itself. So that's the first rule of 1. And then the second, that was this one. The second rule of 1 is that 1 raised to any power is 1, right? And if we examine that and kind of break that down, right, what we see is that, let's say we did 1 to the 52nd power. What we need to do? We would do 1 times 1 times 1 times 1, and we keep going and keep going. What's 1 times 1? That's just 1. What's 1 times 1? That's 1. 1 times 1, that's 1. Doesn't matter how many times we do it. If we keep multiplying 1 by itself, we could do it 1,000,000 times, and we will still get 1. So those are the 2 rules of 1. The first one, if we raise something to the first power, we get the same thing. And the second one, if we raise 1 to any power, then it still equals 1. 1 raised to any power equals 1. Next, we're going to talk about we're going to jump over here to the 0 rule. That's what we're going to jump over to. And I'm going to tell you the 0 rule, and then we're going to come back to the 0 rule after we learn another rule to kind of prove the 0 rule. And the 0 rule says that any number raised to the 0th power is equal to 1. Now that one kind of tricks people up because a lot of people would expect, oh, if I raise something to the 0th power, I should get 0. But no. Any number raised to the 0th power equals 1. So 10 to the 0th power equals 1. 205, that's not 2. 205 to the 0th power equals 1. Doesn't matter what it is. If we raise something to the 0th power, we get 1. So if we raise something to the first power, we get the same number. And if we raise something to the 0th power, we get 1. So moving on, let's do the product rule. So the product rule is basically what tells us how to multiply 2 numbers that are both that have exponents on them. 2 numbers that are raised to powers. And the thing with the product rule is that both of them have to have the same base. Remember, the base is the bottom number. For the product rule to work, both numbers have to have the same base. So here's an example of the product rule. Let's say we had 2 cubed times 2 to the 5th. Do these both have the same base? Yes, they do. The base is what? 2. So what we can do is we could actually expand this out. It's kind of like the proof of why the product rule works. 2 cubed is going to be what? 2 times 2 times 2 times 2. So that's 2 cubed. Let's do it this way. This part is 2 cubed. And then we have times. And then we have 2 to the 5th. 2 to the 5th is what? 2 times 2 times 2 times 2 times 2. So this part is 2 to the 5th. And what you can see is that when we expanded both of them out, all we're left with is a whole bunch of 2's multiplied by themselves, right? So we could just count how many 2's are there. There are 1, 2, 3, 4, 5, 6, 7, 8. 8 2's multiplied by themselves. So this would actually equal what? 2 to the 8th. It's the same thing as 2 to the 8th. So the product rule is like a shortcut, so we don't have to expand that out. Because if we look at the beginning, we could have done 2 to the 3 plus 5, and we get 2 to the 8th. And that's what the product rule lets us do. When the bases are the same, this is the base, right? And we are multiplying, we can add the exponents. So the bases are the same. We're multiplying. We can add the exponents, right? And that is the product rule, or specifically for multiplying. So let's go to the next rule. The next rule, not for dividing. The next rule is actually the power rule, and it's for when we raise a number to two exponents, right? And it basically says that when there are two exponents on the same base, you just multiply them, right? So let's say we had 5 to the squared, or let's say we did this cubed, right? This would equal 5 to the 2 times 3 power, which is 5 to the 6th power, right? So 5 to the 6th power is what we end up getting. And that's as simple as the exponent is. As the power rule is. That's as simple as it is. There's nothing really more to it. We could break it down, but I don't know. Let's break it down. So 5 squared cubed, this would be 5 squared times 5 squared times 5 squared, right? And 5 squared times 5 squared times 5 squared would be 5 times 5 times 5 times 5 times 5 times 5. How many 5s are there? There are 6 of them. And that's the reason why we can just multiply the exponents if we run across this kind of scenario. All right, next we have the quotient rule. And the quotient rule tells us about dividing exponents. Now, with the quotient rule, the thing to remember is similar to what we have to remember with the product rule. With the quotient rule, we have to remember that the bases have to be the same. They have to have the same base. For the product rule and the quotient rule to work, if they don't have the same base, it won't work. They have to have the same base to work. So the quotient rule tells us that if we have something like 3 to the 4th divided by 3 squared, right? The quotient rule tells us that when we're dividing and the bases are the same, we can subtract the exponents. So when we subtract them, we get 3 to the 4 minus 2, because we're dividing, and that equals 3 squared. So let's see if we wrote it all the way out. This 3 to the 4th would be what? 3 times 3 times 3 times 3 divided by 3 squared would be what? 3 times 3. Now here it's all multiplication and division, and because it's all multiplication and division, we can cancel. So this 3 will cancel with this 3. This 3 will cancel with this 3. And what are we left with? We're just left with 3 times 3. And 3 times 3 is the same as what? 3 squared. So you can see that we're getting the same thing. So when we have the same base and we're dividing, right, we can subtract the exponents, and that will give us the correct answer. So that's the quotient rule. Now the quotient rule does give us two interesting situations that arise. So the first thing that the quotient rule kind of leads us to is an understanding of the zero rule, right? So let's say we had something like this. Let's say we had 3 squared divided by 3 squared. So if we follow the quotient rule, what should we expect? Well, we're dividing, right? And the bases are the same, correct? So what do we get? We're left with 3 to the 0, because we need to do 3 to the 2 minus 2. And 2 minus 2 is what? 0. So that's what we get out. That's what we expect to get. But what if we just use our logic or our common sense? What will we expect to get? If I asked you, what is 5 divided by 5? What is 5 divided by 5? Anybody? So
1.
1, yes, it's 1, right? 5 divided by 5 is 1, right? Because anything divided by itself is 1. So if we do 5 divided by 5, what if we did 8 divided by 8? Still 1. What if we did, I always like to use this as an example. What if I had a horsey? That's a horse. Don't judge. It looks kind of more like a dog. A doggy divided by the exact same doggy. What would I get? still 1. Doesn't matter what I have in the top and what I have in the bottom. If the same thing is in the top and in the bottom, you get 1. So when I have 3 squared divided by 3 squared, what should I get? Anybody?
1.
I should get 1. So on the one side, my logic is telling me 3 squared over 3 squared equals 1. And then when I do the quotient rule, it's telling me that 3 squared over 3 squared is 3 to the 0. So logically, what this tells me is that 3 to the 0 must equal 1. Right? 3 to the 0 must equal 1. And so that's kind of a proof for the quotient, for the 0 rule. Anytime we raise something to the 0th power, we get 1. So we did that rule already, but that's the relationship with the other rule. So moving on, the last rule also comes from the quotient rule, and this is just an explanation of what to do with a negative exponent. So when we have a negative exponent, right, basically what we're talking about is something like this. 4 to the negative 2, right? And I'm going to explain to you all a couple of ways to look at this. So one way to look at a negative exponent is that when we do a regular exponent, we are doing repeated multiplication in the numerator. So 4, all the way up. So 4 squared would be what? 4 times 4, right? When we do a negative exponent, one way to look at it is by saying that this is repeated multiplication in the denominator. So 1 divided by 4 times 4, right? Or you could also say repeated division, right? We're repeatedly dividing by 4, or dividing by 4 more than once. And that's basically kind of the idea of what a negative exponent is. But we do need to actually be able to work with negative exponents in a different kind of way rather than the conceptual way. So let me just put a couple more up there, and then we'll look at another way of how we can actually work with them. So another example would be, let's say we had 5 to the negative 3. Well, since it's negative, that means we're doing our repeated multiplication in the denominator. So this is 1 over 5 times 5 times 5. Or 1 over what? 5 times 5 times 5. Yes, we could multiply it. 5 times 5 is 25. Times another 5 is 125. But let's say we didn't multiply it. We could do 1 over 5 cubed. Right? So let's do another one. What if we had 6 to the negative 4? Well, we're getting a similar kind of pattern. We had 6 times 6 times 6 times 6 times 6 times 6, which equals what? I mean, we could multiply it, but we don't have to. We can just write it as an exponent. So this would be 1 over 6 to the 4th. Are you all noticing anything with this negative exponents, what we keep getting? This one would be what? 1 over 4
The 1
squared.
goes over.
Go ahead.
The 1 goes over the new number, the new exponent, I guess.
Yes, and what else is changing?
The negative becomes positive.
And those are the two things that let us convert from a negative exponent to a positive exponent. We move the whole thing to the denominator or to the numerator, right, to the opposite position from where it is, and we change the sign. So if we have something like this, 1 over 15 to the negative 64, what do we need to do? Well, this time our negative exponent is in the bottom. And what did I just say? You move it to the place where it's not, right? So right now it's in the bottom, so we need to move it to where?
The opposite side?
Not the opposite side.
The top.
The top. Yes, we need to move it up top. So we're going to move it up top, and we get 15 to the 64th power. We move it, and we change the sign. So those are the two things we do with negative exponents. So move it, and 2, change the sign, right? So that's what we're doing with our negative exponents. Move it, then change the sign. All right, so that's exponents. Anybody have questions about exponents? Want me to do another example with something or anything like that? Okay, good. So I hope that means y'all are following and not that you all are afraid to ask a question. So let's move on. And if you think of a question later, you can come back and ask me. So order of operations. Now we all probably learned this as PEMDAS. You all remember learning PEMDAS in school? Now I think some of y'all are early child education. Y'all teaching PEMDAS in school?
Yes, I recall it, but we're not teaching it yet.
Okay. Because early childhood, how old is these kids with early childhood education?
Mine are up to 3 years old.
Up to 3? Okay.
Yeah.
So PEMDAS is the order of operations. Now, I always like to think of PEMDAS as like, you know how in Spanish, let's do this really quickly. So in Spanish, let's translate. Any of you all speak Spanish? I take that as a no. So we are going to translate from English to Spanish. So we're going to translate red book. Now, if you look here, right? If you look here for red book, right? We say red book in English. In Spanish, which one of those words do you think means red and which one do you think means book?
Rojo means red.
Negro means book.
Exactly. So you see the order just reversed? See the order reversed? So yeah. So that is like for math, right? Order of operations is like that kind of thing. So in Spanish, a lot of times you put the adjective after the noun, right? In math, order of operations tells us what order to do our operations in. So we start off, we do all of the parentheses. Parentheses are basically like the grouping symbols. Anything that either explicitly or implicitly implies that some operations are grouped together, you should do that first, right? So that's parentheses. Next, you want to do exponents. That's the E, right? Exponents are anything that has an exponent. You want to finish those out, resolve them or whatever, simplify them. Then you do multiplication or division, right? The reason why it's multiplication or division is because multiplication and division are what we call co-equal, right? So because they're co-equal, you actually do the multiplication or division in whatever order they appear from left to right, right? So it doesn't mean multiplication comes first, even though if we look at PEMDAS, the M comes first. It's actually M or D. M and D are on the same level. And the same thing with addition and subtraction. We do addition and subtraction in the order they appear from left to right. Right? So those are just two important notes. So of course we're going to do a couple of examples. So let's come over here. Let's say we have something like this. All right, so what will we need to be doing first? Are there any parentheses? Let's do it like this. Throw parentheses in there. Are there any parentheses? Is anything grouped together?
Yeah.
What's grouped together, Camille?
2 plus 3.
All right, so we're going to do 2 plus 3 first. So what we're going to do is we're just going to write equals, right? And we're going to do 5 squared. That's not changing. Times 2 plus 3. 2 plus 3 is what? 5 minus 15. Right? And then what's next? So let's write out PEMDAS up here. These are literally like our steps, our roadmap. So we did parentheses. Check. Now what do we need to do? Exponents. So next is exponents. So what are the exponents in here?
5 to the second.
5 to the second power. Yep. So we need to do 5 to the second power. Don't forget, after you answer the question, throw it back on mute real quick so that we can not have any echo or anything. So 5 squared is 25, right? Times 5 minus 15. Now what's next? We did exponents. Now we need to do multiplication or division. I want to make them both red. Multiplication or division, right? Multiplication or division tells us to do 25 times 5. 25 times 5 is 125. And we do minus 15, right? Minus 15 is going to be what? Oh,
110.
Now we do addition or subtraction. Sorry. Now we're going to do addition or subtraction. So we do the 125 minus 15, and we get our final answer, which is 110. So following this PEMDAS, right, is very useful, and it's kind of like a roadmap. So if you're ever confused, and you're ever like, I don't know what to do next in solving this formula or something like that, if you ever say that, you just look back at PEMDAS and then break it down, do it one step at a time. So let's turn the heat up a little bit. And I want you all to try this one here. So I'm going to try this one. We're going to have 3 cubed minus 12 times 2 plus 1. That's all going to be divided by 2 to the first power minus 3 squared. Looks like a lot, but that doesn't matter. That shouldn't faze us because we have what to the rescue? We have PEMDAS to the rescue, which is going to tell us exactly how to do it. So first up, well, actually, I want you all to try this yourselves. Try this yourselves. Try to solve this for yourself. Let's see where we get. And as you all try to solve it, I'm going to start to kind of slowly walk through it. So with PEMDAS, first thing is parentheses. So everybody should have jumped right here to this 2 plus 1. And I want you all to do it exactly how I'm doing it, where I start making new lines for each piece. All right, and I'm writing each part on a new line. So first is parentheses. I'm only going to change one thing at a time. So I'm going to do 3 cubed. Where's the parentheses that I want to change? 12 times 2 plus 1. That's the parentheses I want to change, times 3. And that's all divided by 2 to the first minus 3 squared. All right. And what's next? Well, we did PEMDAS, the P. Now we need to do the E. So we look back up at PEMDAS. E stands for exponents. So let's go down here and do all the exponents. So first we did this. Now we're going to do the exponents. That's this here, and this here. So this is going to equal 3 cubed is 27 minus 12 times 3 divided by 2 to the first power is any number. Go back to our exponent rules. Well, let's go back up. What's our exponent rule for 1? Well, we had it up here. Any number to the first power. 5 to the 1 is 5. 10 to the 1 is 10. 2037 to the 1 is 2037. So what's our rule of 1? Any number raised to the first power is
Itself.
Itself.
So that's going to be 2. Very good. And then we have the last exponent, which is 3 squared. So 3 squared is going to be what? 9. All right. Now we go to the next part. So we did the exponents. Now we need to do the multiplication or the division. Put them both at the same level. Now in this case, we got some multiplication in the top. Here's the multiplication. The only division we have is this big fraction bar, right? That's division. But would it make sense for us to divide or to do the 2 minus 9 and then 27 minus 12 times 3 first? Because doesn't it kind of look like, let me use a different color. Doesn't it kind of look like all of this goes together and all of that goes together? Doesn't it kind of look like that? It's kind of implied, even though there are no big parentheses or anything, right? It just looks like that. So this is what we mean by implied groupings. So we actually need to do those first before we do that last bit of division, right? So let's do the multiplication, and then we'll do the addition and subtraction. Then we'll step back to that division. So we have 27 minus, what's 12 times 3? 12 times 3 should be 36.
36.
Divided by 2 minus 9, right? Then we have the addition and subtraction. Only a little bit of that. That's going to be this. That's going to be this. So 27. So 27 minus 36. What's 27 minus 36?
-9.
-9 in the top. And in the bottom, what do we get? 2 minus 9.
-7.
-7. So there actually isn't really any division to do here. We just have 9 over 7. We can leave it just like that. The only thing is we have a negative divided by a negative. Anytime we divide or multiply two negative numbers, we get a positive number. The negatives cancel each other out, and we get a positive, so we get 9 over 7 as our answer. So you can see, when we break it down like this, it looked like a lot in the beginning, but it's actually not that bad. Right? It's actually not all that bad. So it looked like a lot in the beginning, but it's actually not all that bad. Anybody have questions about that? About what we just did there? No? Okay, awesome. So we're going to move on. So that's PEMDAS. Now, again, that piece of multiplication division being co-equals is so critical. So I'm sure last year when people was just saying regular stuff on social media, you might have seen a problem like this going around. Everybody's saying, what's the answer? Is the answer this or is the answer that? Well, the problem comes into play here because we use that division sign instead of using a fraction bar. If we use a fraction bar, there would be no problem, but we use that division sign. We need to remember PEMDAS. We need to remember that multiplication and division are co-equals, so we do them in the order they appear. So for this one here, we start off with parentheses, and we get what? We get 8 divided by 2 times, and 2 times 2 is going to be 4. So we get 8 divided by 2 times 4. And now here's where people get confused because PEMDAS says what? Multiplication is before division. But what did we just learn? Multiplication is not before division. Multiplication and division are co-equals, and we do them in the order they appear. So what do we do first here? Which one comes first?
Division.
The division comes first. So here we have 8 divided by 2 first before we do the 2 times 4. And 8 divided by 2 is going to be what?
4.
4, right? And now we have 4 times 4. And 4 times 4 is going to be what?
16.
16. Now let's imagine we had done the 2 times 4 first. What would we have gotten? We would have been way wrong because we would have been doing 8 divided by, what's 2 times 4? 8. And then we would have got that equals 1. But no, that's wrong. Right? The correct answer is... correct answer is 16. Right? So just a little note. Right now you can correct people if you ever see this problem online. They're like, my professor said multiplication and division are co-equals. Addition and subtraction are co-equals. Do them in the order they appear from left to right. So you can, I give you that power to correct people. Any of you all have questions? No questions? Okay. So that is all we are going to do today. I'm going to stop the recording